Right, I repeat, thanks very much for inviting me. It's a great pleasure to be here. I was told by Mike that if I used equations, I had to explain every symbol. I'm going to cheat, and I'm going to show equations, but I'm not. I'm going to show them iconically, and in so doing, just offer an overview of the how the free energy principle would frame the mathematical structure of the nature of things. Um, it's probably going to be more of a fly past than an overview. So what I thought I'd do is just briefly rehearse the fundaments of this approach, and the ultimate objective would be to understand the scale invariant aspects of self-organization, particularly in biotic systems, through the lens of the renormalization group, and then just skip through a number of applications in the fond hope that we can then revisit those things that the group finds interesting. So I'm going to go very, very fast. Hopefully, go very fast. If I'm going too slowly, Franz, can you speed me up or interrupt me? I do have a tendency to talk too much. So keep an eye on the time and tell me to sort of get to the end quickly if we look as though we're running out of discussion time. Um, so what I put together just has four bits. We're going to start off just by reminding people about the Markov blanket formalism and the Bayesian mechanics that ensue, and then just to illustrate how that works practically using numerical studies, simulating a primordial soup. And then I would normally go on to tell a free energy story about inference and sense making, decision making, but I'm not. I'm then going to go back to a more fundamental question and ask, where do states come from? What is the nature of a state? And the solution to that, or dissolving that question by appeal to recursion implicit in the renormalization group, and showing how that can, a renormalization group can be derived from the very notion of Markov blankets. And then I'm going to hopefully have time to give you three examples of the application of this mathematical image of scale-free self-organization, an empirical one applied to brain imaging time series, a more theoretical one that touches upon previous work with Franz and Mike, and then just a practical application in the context of machine learning and artificial intelligence research. And then probably the most important thing, though, is just to come back to where we started in terms of scale invariance and ask, is there really scale invariance? So that's how I'm hopefully going to end. So starting how I normally start a free energy principle talk with a question posed by Schrödinger: how can the events in space and time, which take place within the spatial boundary of a living organism, be accounted for by physics and chemistry? And I just want to focus on the notion of a spatial boundary, and more generally, any kind of boundary, blanket, screen, any kind of separation or disambiguation between something and everything else, the self in self-organization, or a particle, say, in particle physics. And I'm going to read that separating device as a Markov blanket, as a statistical boundary. For those of you not familiar with a Markov blanket, I tried to sketch out how it emerges from the causal structure, the cause-effect structure of some random dynamical system comprised of states that influence other states, where those influences are denoted by the edges. And if I take a set of states, say my internal states, then I can identify another set of states, the blanket states, that intervene between my internal states and the rest of the world, my external states. And I'm going to subdivide or partition these blanket states into into sensory states and active states, following the simple rule that the sensory states influence but are not influenced by the internal states, and the active states influence but are not influenced by the external states. And I'm going to consider this collection of subset of states as the states that comprise a particle or the self, I repeat, in the sense of self-organization. And just to give you an intuition as to how one can deploy this partition of abstract states of some universe, I've sketched two examples here. This is my favorite system or particle, the brain, where the internal states would be all my internal synaptic activities, and effective connection strengths and the like. My active states would be my actuators or my autonomic reflexes, changing the outside. The external states reciprocate by changing my sensory states and my sensory epithelia that then influence my internal states. But we have the same kind of dependency structure, or cause-effect structure, with this partition in a single-celled organism, where intracellular states can, say, change active filaments that then change the surface states that are pushed out into the external states that are registered by sensory cell receptors, for example, that change the internal states. So at many, many levels, in order to talk about something, one has to define how one thing that is open to the universe in exchange with the universe is separated from the rest of the universe. And that separation is just this sort of interface or Markov blanket, or the inputs and outputs from a systems theoretic perspective. What I want to do now is just ask you to forget about the Markov blanket and just briefly rehearse physics. And then what we're going to do is put the Markov blanket back into play and see what kind of mechanics emerges from that. And we're going to return right at the end to the varieties of mechanics and physics that ensue from this formulation. So I'm just going to start off with a random dynamical system, who is some abstract states that change as a lawful function of where we are in some state space, and plus some random or fast fluctuations. So here, for example, I've traced out what could be dendritic oscillations in a single cell. It could be the phase of my cardiac cycle. It could be me getting up in the morning, having a cup of coffee, doing my emails. The key aspect at any given scale is that this dynamics, this stochastic chaos, or this random dynamical system, is such that I will always revisit states that I was once in. I have some characteristic states of being, and I can characterize that in terms of a pullback attractor, in the sense that I can interpret the density of these trajectories as a probability you'll find me in any particular state at any one time, that, I repeat, defines the kind of thing that I am in virtue of having these characteristic states that I occupy with a high probability, given that I am me. And I've written it down like that because we can apply standard density dynamics here, written as a Fokker-Planck equation. I could have used the Schrödinger equation or some master equation. It doesn't really matter. The key thing is that if this probability density or pullback attractor exists, then we know that its probability density does not change with time. So we can take the solution to our favorite formulation of density dynamics and, crucially, express the dynamics or the flow of these states through state space as some lawful gradient ascent on the log probability of the kind of states you'd find me in. And I've used here the Helmholtz-Hodge decomposition into a dissipative and a non-dissipative part, which is going to be quite crucial here. So I just unpacked this and again cartooned it in terms of the kinds of flows that are always present in anything that has a pullback attractor or aspires at some suitable time scale to a non-equilibrium steady state. And I'm just making the distinction between the gradient flows, the dissipative part, where this flow is proportional to the gradients of this log probability times the amplitude of the random fluctuations. But there's another really important part, which is the non-dissipative, or the conservative, or the solenoidal, or divergence-free part that basically circulates on the isocontours. So the image here is that in order for these pullback attractors to exist, it must be the case that I am effectively flowing up probability gradients to counter the dispersive effects, the dissipative effects of the random fluctuations. But that gradient descent is complemented or supplemented by circular or solenoidal flow. And I'm sort of emphasizing that because, of course, in my world, we deal with these solenoidal or conservative dynamics all the time in terms of oscillations in the brain, in terms of biorhythms, in terms of indeed life cycles, replication. And it may sort of sound odd that I'm subsuming replication and reproduction in this, but from one point of view, and specifically the point of view, say, an oocyte that is destined to become an egg cell, we're just going round in circles The outside is changing, and I'm building people, mothers on top of me. But eventually, I'm going to come back to being in the same kind of state. Um, so now, with this sort of decomposition of the dynamics that are implied just by being a self or by existing as something in some characteristic states at a suitable timescale, what about the Markov blanket? So that decomposition, that Helmholtz-Hodge decomposition, has to apply to all partitions of the Markov blanket, including the internal and the active states. Um, and the story that I would normally tell now is that we can interpret the internal states, so my neural activity or intracellular dynamics, as performing a mixture of dissipative and non-dissipative gradient ascent on the log probability of the sensory states given given I am me. And in a similar vein, the active states are these gradient or Helmholtz decompositions of gradient flows on exactly the same probability. Notice that by construction, these probabilities depend just upon the states that I have access to. They do not depend upon the external states, simply because these states are separated causally from the external states. They're autonomous states. And the story I would normally tell is that we can interpret this joint dynamics as perception and action. And there are many ways you can sort of read this. If I interpret the log of the probability of states that are characteristic or have meaning for me as those states that are valuable for me to be in, then this dynamics here can be read in terms of reinforcement learning, optimal control theory. If I was an engineer, or if I was an economist, it would be expected utility theory. Similarly, if I was an information theorist, the negative of this would be self-information, or more simply surprise or surprisal, leading to the informatics principle, minimum redundancy, maximum efficiency principles, and indeed the free energy principle. The time average of this means that it looks as if I am resisting the dissipative effects of random fluctuations. It looks as though I am upper bounding my entropy. And of course, that's the holy grail of much of self-organization, particularly things like synergetics. And if I was a physiologist, it would be just a statement of homeostasis, just keeping my essential variables within viable bounds that characterize me. The Bayesian mechanics inherits from the fact that if I was a statistician, I would interpret this as a probability of some sensory data given me as a model of how my sensory data were caused. In other words, me as a generative model that would be able to predict the causes of my sensory states, and I'm maximizing the evidence for my model, leading things like the Bayesian brain, evidence accumulation, and predictive coding. So what I want to show now very briefly is just how these Markov blankets are inevitable emergent constructs, and thingness or selfness emerges with any loosely coupled random dynamical system. And the example I've chosen here goes right back about 10 years or so ago now. And what we did here was just build a synthetic primordial soup by having 100 or so little macromolecules, each equipped with dynamics that looked as if they had electrochemical and Newtonian forces, sort of short-term or short-range repulsive forces, and longer, slightly longer range attractive forces, equipping each of them with autonomous dynamics using, in this instance, an Lorentz system, so that we could simulate both the electrochemical status and the Euclidean, the position of each of these molecules as they sort of bubble around autonomously, exchanging with each other according to those equations of motion. So why have I done this? Well, because I now wrote down the equations of motion, I now know the dependency structure, and I can now ask the question, is there a Markov blanket in these simulated states? And if so, is there a little thing living in this soup? And we can answer that quite easily just by reference to a summary of the coupling in terms of the Jacobian, and therefore identify the Markov blanket in terms of the parents, the children, and the parents of the children in the usual way. And this allows me now to identify a set of internal states the blue states here, that are covered by the active states, say the active filaments, that are themselves underlying the sensory states in magenta, exchanging with the external states and showing a kind of non-equilibrium steady state that is characteristic of this little sort of prion or virus-like particle. And then one could go on to show that in fact the dynamics of the internal state do in fact represent events on the outside. But I don't want to go there. I want to ask a question which, if you want to read about this in more detail, is sort of unpacked in this paper on archive. So I just now want to ask a question. What is a state? And I'm going to dissolve that question by appealing to an infinite regress along the following lines. So what's a state? Well, a state will take the ansatz and show that it unpacks ultimately in the right kind of way in terms of the renormalization group. A state is an eigenstate, a mode of a particle's Markov blanket. So I'm imagining here that the state of a particle is captured on the surface because from my point of view, from the outside, everything I need to know about the inside is on the Markov blanket. So, and I'm going to take an eigenfunction or an eigenmode of the blanket states, and that's going to be a state of that particle. But what's a particle? Well, we've already defined a particle as a set of blanket states and internal states. So that now allows us to say, what's a state? Well, the state is just the eigenstate of a particle at an increasingly larger or smaller scale. So here, just to read this out, an eigenstate refers to the amplitude of an eigenmode of blanket states, namely the principal eigenvectors of their Jacobian, namely the rate of change of flow with respect to the state. Interestingly, these mixtures are formally identical to the order parameters and synergetics of the kind promoted by Hermann Haken, and that reflect the amplitude of the slow, unstable eigenmodes that you get just by a separation of temporal scales in any random dynamical system. You could cast this in terms of center manifold theory, corresponding to the slow solutions on the slow or unstable center manifold. But more intuitively, what we're saying here, that there is a natural progression from one scale to the next that is that can be read in terms of the renormalization group that inherits from just having a Markov blanket structure. So I've just sort of tried to schematize that here. Then I start off. Well, first of all, in moving from one scale to the next scale, I have to induce an RG operator, a renormalization group operator that usually comes in with two parts, a sort of reduction operator and a grouping operator. And they effectively write themselves under this Markov blanket partition in the following sense, that if I now want to reduce the dimensionality of a collection of particles, each equipped with internal states and their blanket states in terms of active and sensory states, I can reduce this just by taking the eigenvectors or mixtures, eigenmixtures of the blanket states. And remembering, I don't need to know the internal states because they're conditionally independent from my point of view, from the outside point of view. So that's a nice reduction. And then I've got a new collection of states, but now I can just look at the dependencies amongst these new collection of states and then basically group them together according to the formulation that equips this description of this group of states with a partition that can be read as a Markov blanket, inducing a new particle at the highest state. And then I just start again. I can just keep on doing this and successively coarse grain the description of the dynamics simply by repeated application of this eigenreduction and Markov blanket partition. And the picture that emerges from this is that basically, as you go from a very fine-grained microscopic state level or state descriptions to the macroscopic level, you're effectively just retaining the slow dynamics at increasing scales as you accumulate eigenmixtures of eigenmixtures, so that the fast fluctuations in the eigendecomposition and the intrinsic fluctuations now become absorbed into the noise, if you like, or the random fluctuations, just leaving you with these progressively slower and slower descriptions that are entirely lawful because they are consistent with the definition of something at each and every scale. So when you apply this reduction, these RG operators to that synthetic soup, you can sort of start off with 128 little particles or macromolecules and reduce them to 18 particles at the next scale up and ultimately repeat again. And it turns out that, in fact, that soup can be partitioned or behaves as if it was just two particles. That's a bit of an abstract example, so I just wanted to give you now a practical demonstration of how this can be applied to real systems. And in this instance, what we've done is taken the dynamics of brain activity using functional magnetic resonance imaging at each of, say, 10 to the 4 little cubes of the brain, measuring the dynamics in terms of the hemodynamic responses. So there are sort of 1,000 or so little patches of the brain here with this distance matrix separating them. And we can work out on the basis of the dynamics, the connectivity, the coupling between each of these voxels, another word for volume elements. So here's a distribution of distance, and here's the sparse connectivity that ensues when you actually go in there and ask or estimate the coupling, the influence of one little part of the brain on another part of the brain. And then we can just apply those RG operators that I described in the previous few slides to coarse grain the brain in a purely data-led way using that eigenreduction followed by the Markov blanket partitioning and implicit grouping. So here's the first level. We've got 124,024 states and particles, and I just showed a few examples of these little particles here. The grouping is predicated on the Jacobian, the rate of change of the flow with respect to the states, which is interesting because the eigenvalues of this now give you the natural time constants for each of the particles and indeed the scale. And I'm just sort of illustrating the time constants here in terms of the eigenvalues of this Jacobian or dynamical coupling matrix. So we can take the ensuing states from this one and just reapply this RG operator, and we now find that we can carve up the brain into 57 particles with their associated Jacobian and their associated time constants here in seconds, here about 10 seconds. These are the sort of the spatial aspects of these particles, carving up the functional architecture of the brain into a coarser representation. And we can go even further. And at the next scale, we're talking about 5 particles or things that are all coupled to each other and but are separable from each other with their characteristic time constants here. So the interesting thing about this is I can now go back and ultimately here's just one particle with its time constants. I can now go back and just look at the empirically the scaling laws that underwrite the scale invariance that has been obtained through repeated application of these RG operators. And by scaling laws, what I'm saying is there's a notion of something called RG flow, which basically maps some key variables, in this instance, the rate constants or the characteristic time lengths and actually space lengths, maps from one level to the other level with a scale law here, denoted by beta here. And what that means is I can go back and at each of the levels measure the characteristic time constants on the basis of the eigenvalues and the space constants implicit in the spatial separation or the spatial scale at each level, the size of these particles, and then plot the log of those two things against each other to identify my scaling law. And here are the empirical results from the four levels that I've just shown you. The thing that the reason I wanted to show you this is that you can play a really interesting game and sort of extrapolate to very, very, very large macroscopic timescales and space scales, or go right back down beyond the regime that we've actually empirically used to identify this scaling law. And I'm now going to go back to the Bayesian mechanics just to make the point that if the brain is in the game of, if it's a Bayesian brain, then its dynamics must in some way install the scale invariance of the universe in which it lives, which means that just by looking at that fMRI, functional magnetic resonance imaging time series, I should be able to deduce the different scales of organization of the world from which that brain came. And that's been done in this, that's summarized here in terms of somewhat fanciful applications of that scale law. So this is the range of space and time over which the brain was operating, the data were generating the evidence for this RG flow or scale in power law. So, from a few hundred milliseconds and a few millimeters right through to seconds and up to, say, a decimeter. But just applying and just looking beyond that, what that suggests is a characteristic sort of space-time scale that reaches right down and is very consistent with the fact that, for example, dendritic spines occur in density about 5 per micrometer, and have dynamics that unfold on the order of a millisecond, right the way through to very big things, something, say, zero point 0.3 of a kilometer, that would have a typical time constant in the order of a few days, such as an international scientific conference, with intermediate values that do reflect the scale invariance and the scaling laws of self-organization that our brains certainly are designed to cope with. So I promised you a theoretical application of this. This is slightly coerced, just as a nod to Franz and Mike, and Chris. But I think sort of serves its purpose. One can apply this notion of coupling between different scales in many different contexts. This is an attempt to deploy this idea in the context of theoretical biology, and in particular, sort of a variational sort of neo-Darwinian synthesis, where we're treating kinds of things as an extended genotype at the higher level, and associating, for example, the genotype with the internal states, that provides a context for faster dynamics at a phenotypic level in terms of the extended phenotype that possesses its internal states and its Markov blanket, and is in exchange with other things here denoted by the external states. So suggesting that even at an evolutionary level, you can get this sort of this a renormalization group in the sense that the dynamics of this partition at this scale have exactly the same functional form as the dynamics of the and have implicitly the same Lagrangian, the dynamics at this scale. It's just that this scale is much slower, and therefore, if you like, provides some context for the fast dynamics that unfold. And as the fast dynamics that unfold, you get the bottom-up causation in terms of these eigenmixtures, or most the mixtures that show the most variability, but typically over a slower time scale. And you can make all sorts of interesting arguments about this in terms of selective pressure and adaptive fitness, where the variation free energy bound on that surprise or model evidence or marginal likelihood uh, plays the role of an adaptive fitness. And the example that I wanted to work towards was very early work with Mike that Franz subsequently pursued, and a very simple example of this where the highest level is actually frozen at a fixed point attractor. So the ultimate example where we've um, implicitly use an adiabatic approximation to say that the genotype is so slow it's stopped moving. So let's just now see, look, how can we contextualize activity at the lower level? And the key thing in this example was we were trying to explain morphology, how different cells self-organize together under something that is inherited from the scale above, which in this instance is a genotype, and it is a genotype that implicitly encodes a generative model on the inside that enables lawful behavior in exchange with other things that share that generative model. I won't go into any detail, but what it allows you to do using numerical analysis is to simulate self-organization of multiple cells that are pluripotential and share the identical genotype, and from the point of view of the Bayesian mechanics, the same expectations and generative model about what they should sense and how they should um, respond to those sensations. Where you can now read the generative model as a template, which means I've got to find my place in some template morphology whose free energy minimizing solution just is the target morphology that's now been specified by the scale above, namely the genotype. And then finally, a practical application. There is an increasing awareness in machine learning and artificial intelligence um, that many of the nature of the deep networks implicit in deep reinforcement learning, for example, or any deep model that has this hierarchical structure, lends itself to an interpretation in terms of these renormalizing dynamics that can be read, from my point of view at least, or the free energy principles point of view, as an inference or learning process, simply because you're maximizing your model evidence or minimizing your bound um, on the surprisal. And we sort of took that to its limit in terms of growing generative models under a renormalization group so that they were renormalizing, such as you move into deeper levels of the generative model in and of itself. For example, the different scales that we saw in the fMRI example. Not only do we cover more space here in terms of a sort of spin block um, um, style, but also more time. And I try to cartoon that here in terms of the form of these generative models expressed as probabilistic graphical models in this instance. But crucially, as you move through time, generating observations through some likelihood mapping, given your representation of the outside states by your internal states, you do so more quickly at a lower level than you do at the second level, and which is much more quicker than at the third level, and so on. So if you imagine these things occupying some centripetal architecture, what one way of thinking about this is that for every tick of clock or universal time, there are lots more things happening at a finer scale at the interface with your content or your the thing with the sensors, for example, if in robotics or drone control, than what's going on the inside, which updates very much more slowly, effectively representing the context in which the faster updates are occurring with reciprocal message passing between the two. Um, this has some interesting properties in terms of um, minimizing free energy or maximizing model evidence, which translates into minimizing information loss, which speaks to the compression, generative models as compressing things. And this is a simple example illustrating how one can build a simple two-level renormalizing model in a way that allows it not only to encode some dynamics. Here, a short video of a bird flapping her wings, but also to generate it and to recognize just with partial cues. So this is fast dynamics at the first level, and then the slower dynamics at the second level, and just to demonstrate the utility of having a generative model of content, in this instance, sort of a pixel array. We gave it this stimulus, which is just a partial view of a bird flapping its wings, and then ask, could it fill in the gaps on the basis of its inference or its Bayesian mechanics or its generative model that has this renormalizing aspect? And this is the results that within a couple of frames, it's quite able to generate and infer what's happening everywhere, even though it's just seeing the upper quadrant here. So I've got to the coda. The question now is this scale invariance, does it just keep on going forever, or all the way up, or all the way down? And I just want to come back to this Helmholtz decomposition and make an interesting observation that perhaps no. In virtue of the where we started, which is this solution to the density dynamics of any random dynamical system, that depends upon the amplitude of random fluctuations gamma here. That implies that as we get bigger and bigger and bigger and we move to more macroscopic scales, these random fluctuations will average out, and there will be a transition from a physics or a mechanics where the random fluctuations are large in relation to the conservative or non-dissipative part, to a situation at a sort of the scale of heavenly bodies where there is no random fluctuation, say in the position of the sun, relative to its conservative solenoidal circular motion. And what that basically means from the point of view of all of, as I sort of intimated that this is all of physics, is that you can now look at the limit cases of this and situate the Bayesian mechanics and the self-organization that we've been talking about, that is characterized both by a dissipative and a non-dissipative part that licenses this notion of Bayesian mechanics and implicit self-evidence or model evidence maximizing description of the dynamics. So if we set Q to 0, we're just basically left with this solution being formally equivalent to the time-independent Schrodinger equation, and as such, an apt description at one level of quantum systems and hence quantum mechanics. We could take this level, and I should say that this arises just by taking the complex root of the probability density. We could also just say, well, let's assume we've got lots of very, very small things. What would happen then in the absence of any non-dissipative or conservative dynamics? Well, what we get then are integral fluctuation theorems that underwrite statistical mechanics, or more specifically, stochastic mechanics. But if we now allow or admit a mixture of solenoidal and non-solenoidal or dissipative mechanics, then we get and apply it to the Markov blanket, we get our Bayesian mechanics. But if you go too far and eliminate the stochastic part, we end up with classical mechanics, Lagrangian mechanics, that simply just have this sort of solenoidal divergence-free, non-dissipative aspect. So that suggests to me that there's a sort of Goldilocks regime where you've got to have both the dissipative and the non-dissipative parts in order to have the biorhythms and the life cycles, and to have this kind of itinerancy that we've been talking about. And that strikes me as very similar to Prigogine's notion when writing on dissipative structures. Only when a system behaves in a sufficiently random way may the difference between the past and future, and therefore irreversibility, enter its description. And the difference between the time irreversibility is just a statement of the existence of this divergence-free or solenoidal component to the dynamics. And with that, I'll summarize it with the fleas, greater fleas have little fleas upon their backs to bite him, and little fleas have lesser fleas, and so on ad infinitum, which lends, to my mind, the notion, again, a quote from Prigogine, complex systems do not forget their initial conditions, they carry their history on their backs. And with that, I think it just remains for me to thank those people whose ideas I've been talking about, and of course, to thank you for your attention. Thank you very much.
Thank you so much, Karl. It's great. So any questions here?
Can I ask a question?
Yeah.
Yeah. So I was really inspired by the Helmholtz decomposition idea, and I just wondering, do you have any literature about this thing? Because I really want to read in detail about that.
Yeah, that literature. I mean, you obviously you'll find lots of literature on the Helmholtz decomposition. It's
Yeah, sure.
that's
Yeah, my question is about the using Helmholtz decomposition and its connection to something like invariance of distribution.
Yeah, I mean, if you want a technical overview, then the particular physics monograph on archive, which it's never really been published, but that would be the best place because it's got all the relevant references in. I think if you just want to, to situate it in the grander scheme of things, the, there's an increasing interest in that particular decomposition, which has been generalized from three-dimensional state spaces to an arbitrary high-dimensional state space called the Helmholtz-Hodge decomposition in the 1990s. And that's been taken up by people in machine learning in the past 5 years as a potentially important way of understanding dynamics that could be harnessed to do some kind of optimization. Usually what happens is that these people are students of a gentleman called Ping A.O., Ping-A.O., and he has been telling this story for about 10 years, 20 years. And if you look at his literature, you'll get a sort of interesting. You can see how this idea was generalized and and applied to many different fields, sort of either in terms of sort of right from evolution through to cancer. So there's an interesting paper trail from a number of different directions, depending upon what your tastes are.
Yeah. We recently have a paper. I think it's very close to what you just mentioned. We want to use the hypothesis that the distribution does not change, but the underlying dynamics is changing very fast. So we have a preprint I shared in the chat, and I'm not fully understand what you mentioned about the decomposition, but I think it's very close because we are trying to finding such dynamics that recover the ground truth of the dynamics. But yeah, I will write email to you and maybe we can discuss later.
Yeah, well, that sounds exactly the same. And, when I talked about the solution to the solution to the density dynamics, that's it. What flows must be there as
Yeah.
if you've attained some quasi non-equilibrium steady state. That is the solution, and you can always write down that solution in terms of the Helmholtz-Hodge decomposition, which leads to the story that I was telling from sort of the point of view of biotic self-organization. So it sounds very similar. Yeah.
Thank you.
Doug, please go ahead.
Oh, me? So I understand the approach of finding Markov blankets inside of Markov blankets inside of Markov blankets so that you get this hierarchy. If you're then going to look at a time course, you have to decide that, gee, this is the same thing, but just at a later time. So it may have changed in some way, but I'm going to still say it's the same thing. So, like as a specific example, if I put on a COVID mask, my daughter's dog no longer recognizes me. And yet we know. And so is there something in this formalism that contains this distinction between what is absolutely required for your definition of this thing and what is allowed to change?
Yeah, that's a brilliant question. And it is answered in two kinds of way. The first way would be the kind of answer you'd get if you were working with people on Markov blanket discovery algorithms that allow now for the Markov blanket itself to transmute and to wander around. So it's important to realize that the Markov blanket, the thing that separates and defines something, is itself a random variable. It's a statistical object, and it can wander around in the spirit of Birkhoff's wandering sets. So you have this notion that Sorry, I'm smiling because I often worry about this whenever I cut my hair. I've changed my Markov blankets or cut my toe or eat something.
Yeah.
Um, so a lot of people would answer, yeah, no, you have to, you can only define the Markov blanket in a limited time frame, or you have to allow for the Markov blanket itself to move, and that would require a different kind of mechanics. The second answer is probably the one that you were implying by your question, which is at the moment the answer I prefer because it's more of a solved problem, which is the separation of temporal scales. So the whole point of having this renormalization group is that the Markov blanket at any one scale only lasts for a period of time over which things do not change at the higher scale by appeal to an adiabatic approximation. So the whole point of having this sort of temporal dilatation or separation of temporal scales in this renormalization approach is that you can now license a definition of a non-equilibrium steady state that only lasts for a very short period of time. And then what do you mean by a short period of time? Well, I mean the period of time over which the scale above doesn't change very much. And that means that you now have, if you like, a view of the scale above as providing the context in which things exist for a finite amount of time. So we're not talking about true ergodicity. In fact, by definition, this renormalization group approach precludes ergodicity in the mathematical sense, that things are fleeting, but they're only fleeting from the point of view of the level above. From the level from me, even while I'm cutting my hair, I still exist in some recognizable states and some recognizable sort. But from an evolutionary point of view, I'm very transient and I will decay at some point and I will come into being at some point.
So that's an interesting way of looking at it. Kenneth Denby and I used to have a conversation about this in a question, so it was related to time. But you would say, as a biologist who used to be a physicist, I would say, well, okay, there would be some property of this snowflake or whatever that must be the case, otherwise it's not a snowflake, and other properties that could change. And in which case you would say, okay, the property is set, and any changes you get, the temporal changes, are just an empirical observation. The other way that you're sort of looking at it is, okay, the temporal time scale is what's going to define all this, and whatever physical property happens is just the empirical observation.
Yes, absolutely. And the snowflake is a brilliant example, and it is exactly, what it would be to be a snowflake ties you into a particular kind of state space, which is just that pullback attractor. Yeah. So that sort of log probability density, that surprise or self-information, whatever, log model evidence, that's just a description of I have to be in this configuration that is defined by a high probability in this state. But there'll be other dimensions that don't restrict me. I could be a snowflake in Milton Keynes. I could be a snowflake in Boston. So there are other dimensions where there's no constraints, but there are certain sort of privileged states of being that are just defined probabilistically with that pullback attractor. Yeah, absolutely.
Oh, then I better ask, and then I'll be quiet. Is the scale invariance always the case, or is that an empirical observation?
I'm not sufficiently fluent with the maths in terms of what it would require to be a member of the renormalization group. But the thing that I illustrated was an empirical observation, but it is usually the case that in any system to which you apply these RG operators, you do get a scale law that can be characterized by an RG flow or a beta function. So people just search for the power laws using some kind of RG operator. We do know that there has to be an ordinal structure. So by construction, and specifically the construction that I sort of briefly rush you through, the eigenvalues of the Jacobians that determine Lagrangians or the functional form of the dynamics have to be ordered. So one scale has to have a numerically smaller, a larger negative value than the next scale, and the next scale. Whether they have a lawful beta function or RG flow, I don't know that that comes out of the maths, but they certainly have to be slower, as it were.
Thank you.
David, please go ahead.
Yes, thank you very much for your talk. I'm interested in this possible applications of your work for the relationship between the morphospace and the bioelectric field or the bioelectric network of an organism, or like a multicellular group of cells, deciding what shape to make themselves into over time. Can you discuss a little bit about that? If we can think of the morphospace as this abstract mathematical structure somewhere, I don't think it's in Platonic heaven, but I'll say it's in the universe, wherever it is. And then the bioelectric network tracking this through these processes that you've described in your talk. Can you say a little bit more about if that makes sense? Thank you.
Yeah, no, well, it makes absolute sense, but I'm looking at this through Mike Levin's eyes, really, and the original motivation for the little demonstration I gave you was precisely that. It was precisely how do you how can you show that morphogenesis or pattern formation or self-assembly at a cellular level is an emergent property of there being at some other scale some some pattern, some structure that in this instance was encoded genetically or epigenetically at the scale above in terms of a genotype. And how would that be realized? I mean, there are a number of levels in which one could sort of describe or unpack this. Perhaps one intuitive one is that given this abstract pattern, this Platonic form that is basically inherits from the scale above, these slowly fluctuating genotypes, for example, that themselves are also contextualized at even a higher level. But from the point of view of a single cell brought into being, the template or the generative model implicit in the genotype has everything that is necessary to be unpacked at the faster time scale in order for the cells to find their place. And in finding their place, they then basically minimize their surprise about the electrochemical signals they are receiving under their generative model that they all share and have inherited from the scale above. So that basically that sort of joint synchronization or joint minimization can only be realized when they've all found their right place. And to my mind, that that kind of simulation was really insightful for me. In the sense that I have to be in the right place to generate the kinds of signals that you would be not surprised about under your expectations about how things should be deployed. Um, um, but you have to be in the right place at the same time to receive them, and you have to be generating the right signals. So the only solution is when we're both in the right place together, even though we have exactly the same generative model or sort of epigenetic script for this kind of realized self-organization, which, as you say, is probably best understood in terms of bioelectrical signaling and or chemical gradients.
Can I ask a follow-up question? So, I've been thinking about this, that there must be some kind of feedback from the morphospace to the cells so that they must be able to sense, they must have some sensory abilities to know when they're the correct shape they're supposed to be. And like you said, the surprise element or whatever we're talking about, that they're going to the. So is that an important part of this whole idea that there's a feedback mechanism of some kind that they know when they're where they're supposed to be?
I see. Yes, no, absolutely. I missed that element out. Yeah. So this the morphospace, if you like, encoded by the genotype, has a certain pluripotentiality. So it means that it has to be apt for specifying the behavior if you end up here. And that all that means is if I'm a little cell, all I need to do is to infer where am I. And if I know where I am in the morphospace, I can just go and look at my generative model and say, what would I expect to sense in terms of pressure from neighbors or signals from neighbors? And also, what would I be expected to broadcast from? So I have to basically infer where I am in the morphospace on the basis of the signals that are provided by other things like me doing exactly the same thing at the same time. So yes, now I remember that was why the paper was entitled Knowing Your Place. It was that inferring where you are in this morphospace in order to do the right thing, to generate signals for other things like me, who are using those signals to infer where they are. So jointly, we all know we're in the right place.
Thank you.
Karl, it's almost 1 p.m. Do you have more time for a few questions or?
Yes, of course.
Great. All right, Patrick, go ahead, please.
Right. Hi. I study memory and learning in cells, and I've been thinking about, what memory is in my limited understanding of the FEP, and I was hoping you could tell me if this makes sense. So, from what I understand, an organism needs to deal with its environment in order to survive, and it does so through its generative model, which is basically a compression of its experiences, both its own lived experiences and evolutionary history, I guess, um, which is a sort of memory of what its world has been in the past, which allows it to deal with it in the future. So my main question is: does it make sense to say that the generative model is its memory, and that memory is prediction?
Yes, I think that's absolutely right. And it's mathematically, the generative model, you're absolutely right, will have aspects to it that are played out at different time scales. So normally people will talk about the structure of the generative model. And then once you've got the structure, say, the structure of your DNA or the number of levels in a variational autoencoder or the number of states in a discrete state space model. Once you've got the structure, then you have to parameterize. You have to equip the structure with parameters, say connection strengths, or a particular code, or parameters of equations of motion in the state space model. So these parameters don't change very, very quickly. They are, for example, during a short lifetime of a particular model, they'll probably be time invariant, but its life will come to an end and its structure may well be replaced with another structure. And then that generative model now is in play. And when you invert the generative model in the face of data or interactions with other cells, for example, you'll be doing inference. You're now inferring the latent states, the dynamics of the latent states who evolve or that evolve given the parameters under the structure of your generative model. So the inversion of this kind of generative model has three nice parts, which you've actually just articulated very clearly. You've got the inferring under this generative model your latent states is just inference. It's sense making in the moment. Optimizing the parameters of your generative model, which is just a free energy minimizing process, but at a slower time scale from the point of this renormalization perspective, is just learning. So it's installing the regularities based upon your inference about states, those constants, those time invariant contingencies and laws in the parameters of your generative model, which could be, say, like connection weights. And then you've got the third level, which is from time to time at an even slower time scale, you're going to do Bayesian model selection. And of course, if you're a theoretical biologist, that would be just natural selection, where you are selecting those structures, those phenotypes that have the greatest marginal likelihood or model evidence of populating this eco niche. together with other things like like that. So I think this that question again speaks to a really nice separation of timescales from a very pragmatic point of view. As a statistician or somebody in machine learning, inference fast, learning slow, selection sporadic and very slow. But they're all trying to minimize the same kind of quantity, which is the marginal likelihood as bounded by things like variation-free energy, or which is the same as the model evidence. And that, from a biological point of view, looks like sort of inference and reflexive responses, decision making in the moment, through to learning, through to natural selection. Or you could argue that the Bayesian model selection actually occurs at a developmental timescale. And then you get into interesting sort of issues about, for example, sleep or critical stages in neurodevelopment, where you can do sort of Bayesian model selection on the fly. So there's a nice set of theories about why we sleep, for example. Why do we sometimes completely sequester ourselves from the sensorium? And of course, there's no inference anymore because there's no data to make any inferences about. But you can still optimize your marginal likelihood or minimize your variation-free energy by changing the parameters of your model, by basically dropping out redundant connection strengths, for example, in the spirit of synaptic homeostasis. So that's one argument for why things sometimes take themselves out of the game and just do a bit of house clearing, in terms of minimizing the complexity. I should just add, just to make sense of that, the logarithm of the evidence, the negative value of which is the self-information, which is bound by the free energy. The logarithm of the evidence, the marginal likelihood, is equal to accuracy minus complexity. So and what that means is that it look as if in maximizing your log evidence or your evidence, it looks as if you're trying to find an accurate account of something as simply as possible. But if you go to sleep, or you take yourself offline, or if you're asleep, for example, there is no accuracy because there's no data to fit. So you can just minimize the complexity just by it could be thought of. You could think of that as a kind of learning, but I think mathematically that would be more like model selection, in a particular context.
Penter, do you have a question?
Thank you, Karl, for your talk. It's always a pleasure. You showed us how the RG formalism could be used to recover the dynamics of the bird flapping its wings while it's in place, right? So it reminded me of the case of murmuration. The starlings flock together and they change shapes. But the shapes don't really seem to cycle. No, they seem to constantly change shapes all the time. So do you think the scale invariance exists in that sort of dynamic, and if or the origin formalism could be used to recover the trajectory of the flock? I have a feeling that Karl is gone.
Does look like it. It's not just you.
Okay.
We'll give him a
Darn.
couple of seconds to come back.
Excuse me. Franz, I'll ask you a question since you're the resident expert while we wait for Karl.
Sure.
So all of the renormalization that he covered, correct me if I'm wrong, because it may be wrong. A lot of it is based in space, right? This is like spatial renormalization, especially when we talk about morphogenesis. Like it was always like, particles coupling, and it seemed like it was always coupling via like the spatial component. Is that correct, or is that an overstatement?
I think so on the individual layers of that hierarchical Markov process is correct. I'm not quite sure myself if afterwards, when you construct this big hierarchy of different scales interacting, or whether or not you apply some renormalization in time as well. But generally, because all of these are Markov processes, you don't really do a bunch of time renormalization.
But I
I
think
was
we
wondering.
did time
Oh,
renormalization as well, right? Because it starts with dynamics, and then you have the Jacobian, and you do the eigen factorization. So from that, you recover the time scale of each layer. So when you do renormalization on space with dynamics, you can recover the time
No.
scales as well, right? Yeah. Oh,
Karl's
very
back,
nice.
so we can ask him the question.
Sorry
Okay.
about that. Yeah, I lost connectivity, but it's now returned magically, so that's quite good.
Right. Karl, so I was asking about how you showed us how the RG formalism could be used to recover the dynamic of the bird flapping its wings while it's in place, right? So it reminded me of the case of murmuration, where you see the starlings flock together as a group, but the shape of the group itself, keeps changing all the time and doesn't quite seem to repeat itself. So do you think that there is some sort of scale invariance in a situation like that? And do you still think that the RG formalism could be used to recover the trajectory of the shape of the flock? Because it's not quite steady state, right? So that's my question.
Well, that's an interesting question. I haven't thought about that, but yes, in principle, yes, you could coarse grain an ensemble of birds into a swarm, and then compute the dynamics of the swarm, and then create a generative model. Usually be a state space model of the swarm behavior, and then that would certainly enable you to predict the itinerancy and the characteristic shapes of the swarm in and of itself. And I'm just trying to think of applications of that. I don't know of uh, any applications directly where you are focusing on a generative model of the itinerancy, the chaotic itinerancy that would be implicit in these kinds of models. Other than some work done by people like Connor Hines, who is an expert in ethological collective behavior, um, and his colleagues. But there was a paper in PNS about a year ago now, applying it to shoals of fish and how their collective behavior can be understood as emerging from simple local interactions, and then trying to characterize the collective behavior in terms of groupthink, in terms of deciding whether to go over there or to go over there. But what I'm thinking about is more the work in multi-agent modeling, and trying to understand societal organization in terms of spreading beliefs and committing to particular memes and the like. So there is a little bit of work in that space. And as you say, it all rests upon the functional form of the generative model. And if you've got a state space model with dynamics, which you will have if you want to look at belief updating processes by definition, in with a separation of temporal scales, then you should have a description of of collective behavior at some scale.
Thank you.
Well, so go ahead.
Karl, I had a quick question, and you can tell me if it's a misunderstanding from the get-go, because it may be a lot of the coarse graining that you were doing throughout this relied on like spatial coarse graining. So like coarse graining local particles together into systems up and up and up and up.
Yeah.
And I was curious if you were familiar at all with it's a neuroscience paper with David Tank and Linoy Meshulam, where they do this kind of coarse graining, iterative coarse graining on a set of neurons doing calcium signaling. But rather than doing it on space, they do it on correlation. So you take the correlation of two signals across time, and if they're correlated, you kind of add them together, and you keep going, and it lets you coarse grain and evaluate the system at different levels. And I was wondering if it's appropriate to start thinking about some of those topics if you're familiar with it, with some of the things you've presented today, or if it makes sense. Or
No,
if
no,
that's
it
a
makes sense. It's a really important because there is no unique Markov blanket partition, and I
okay.
think what your question speaks to is, well, how do you, in a principled way, do that partition that is necessarily part of the grouping operator that would require a complete coarse graining, and that's a really delicate question. But before celebrating your potential answers. I think it's worthwhile remembering that there are not an infinite, but certainly a large, if countable, number of ways of partitioning things. And even at any one scale, even before you move to the next scale. So there is no unique way. You have to pick the scale and you have to pick the the procedures to do the Markov blanket partition. And just to come back to your specific question,
Hmm.
once you've identified the internal states, everything's straightforward. You then identify the blanket states just by reference to the conditional dependencies or the coupling, without reference to space. And once you've identified the blanket states, you take that part off the table and start again. But in starting again, you now have to identify the internal states. And if they're more than one, how do you do that? And the spin block, the physicist's approach would be under the understanding or the assumption that most systems, even in active matter, the dependencies, there is no action at a distance. So it all depends upon my neighbor. Of course, this would be no good for bioelectric signaling, but in in
Yeah.
a simple soup, you can assume local interactions. You can use spin block spatial partitioning, but that's not going to hack it in the more general way. So much of the early work that I was showing from the Life as You Know It paper, that actually just took the principal um, component from an analysis of the correlations to identify a set of internal states, which sounds very close to the procedure you were saying. And I
Okay.
should say that most recent applications of machine learning also take that tack. They ignore space and they find the set of local voxels or channels that have the
Mm,
highest internal mutual information. Um, Often they are together in space, but sometimes they're not. And and that would be another way of uh, finding a principal way of identifying your internal states
okay.
before you can define your Markov blanket.
Nice. So thank you for restating my question in a much more elegant way. That's great. I'll have to write that down. So do you think, I mean, of course, there's an infinite way for us to potentially partition things. Do you think functionally this is important? Like, do you think if I'm a neuron, I'm part of like three functional partitions and they are all working together? If that makes sense. Because that's quite confusing. Because then how as an investigator am I supposed to figure out one, how do I partition just to analyze it, but two, functionally, if you're part of three functional partitions all interacting and participating together, it almost seems like an overly gargantuan task to disentangle all the things that are going on.
Well, yeah, I'm smiling, but of course that's the task that we as scientists and biologists are facing. We have to identify those function structure mappings that answer exactly your question. Yeah, but I mean that's why you're an expert. You're an expert in being able to define those Markov blankets and to define the things that matter that have that sort of functional segregation. Um, imagine that your field of study was the kind that people would confront if they were studying active matter. So there are no discernible boundaries. It's just a soup. There has no structure, has no form, has no sparse coupling, other than that local interactions, which of course is sparse. But so I think that every field of inquiry basically the answer to your question is yes, absolutely. It's really important to identify the boundaries that matter from a functional point of view to understand the delicate structure. And of course, that delicate structure is what defines you as an expert in this field or that field. For me, it'd be neuroscientist. For me, it would be functional anatomy and functional specialization in the brain and its modularity and getting the right scale. Do I talk about brain areas? Do I talk about cells? Do I talk about neural populations? I may be a neurologist and more interested in the sort of the cerebrovascular structure, a different kind of function. But whatever, I will have a way of identifying my Markov blankets in this sort of in this applied sense. Yeah, so I didn't mean to oversell the degeneracy of partitions.
No.
Usually, you know, I think Jeff. I'm not quite sure what Jeff Beck is doing now, but certainly he was working um, in the past few years with colleagues on Markov blanket discovery algorithms. So there is a tech and a maths out there that basically says, I'm going to use the Markov blanket structure as a generative model to make sense of my data. And therefore, I should be able to identify things in my data. So if my data truly has 3 bits of a cell, that should be emergent from the dynamics that report the coupling and implicit or consequent conditional independencies that allow me to define the Markov blanket. So you might want to look at his more work in the past year attempts to do that. So interesting attempts. He actually applies it to a flame.
Mm,
Can you identify if the flame is a thing and if the flame is moving? And it touches on an earlier question about do Markov blankets move around?
right. Okay.
Yeah.
No, this is interesting. Thank you, Karl. I appreciate it.
May follow up on that, Karl. The expertise comes in posing the right possible Markov blankets, essentially asking the right questions. But you can use something like Bayesian model reduction or other algorithms that compare different algorithms that you have based on the data you're supplying it. That's how I interpret things like dynamic causal modeling essentially working, right?
Yes, absolutely. Yeah.
Okay. And then I had another question on your last point that you raised in your talk, which was the fact that you need to have some kind of random movement, some kind of random processes in your dynamic system. So you get this fluctuation term, which allows you to get time and irreversibility. And this may be a naive question, but take the example of the billiard pool table, and you have where you set up and you break the balls and they'll go everywhere. To an approximation, there's no randomness in there, right? It's all classical physics, and yet it's very easy to tell if you play this video in reverse which one is the actual sequence of events and which one is the reverse. Can you comment on that? What am I missing in this
Well,
paradox?
yeah. Well, when you're playing pool, you have to incorporate your floppy little body and all its stochasticity into the equation. So the consequence of any of you moving or knocking the billiard ball, um, coupled with, of course, the metastability. Well, not metastability, but the sensitivity to initial conditions, which is amplified by even small amounts of stochasticity, means that there's a lot of indeterminism. So I was really talking about the 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 stochasticity that disappears when you coarse grain a universe to the extent that I can now describe my universe in terms of the location of massive heavenly bodies, for example. It's that kind of scale that we're talking about. You could argue that it might be at the scale of certain meteorological events, but I think there's too much itinerancy. Sorry, there's probably too much stochasticity even at that scale, but I may be wrong. But certainly when it comes down to our scale, sort of meters and seconds and the like, I don't think you can take stochasticity out of the equation. But there's an interesting qualification here. When you drill down on the maths, the thing that keeps you and me or the thing that equips us with a sort of generalized homeostasis is the fact that our blanket states and internal states are incredibly precise, or there is a level of description that renders them incredibly precise. So, for example, I may, each degree of freedom in my lived world may be encoded by a neuronal population with, say, 10 to the 4 or 10 to the 5 neurons. And in virtue of the fact that I can now apply some exchangeability and coarse grain those 10 to the 5 neurons into one average value, for example, I can render a certain level of description of my neuronal dynamics almost noise-free, very, very precise. And that's a necessary condition to understand free energy minimization in terms of this homeostasis. So just minimizing your free energy in and of itself does not give you a low entropy state of being. You actually have to have, as part of your generative model, the belief that I am the kind of thing that has a very low entropy state. I have very well-defined states of being, and I only do certain kinds of things, which leads to this notion that you've got things like you and me that are almost deterministic, very, very precise dynamics, carefully crafted, reproducible, that are confronted with a very capricious stochastic world. So you've got these really sort of cool things in a hot world, which means that the joint system now has some stochasticity and you can have some gradient flows and probability distributions, but the actual dynamics themselves on the inside and in terms of our sensory registration of that world are actually very, very precise, which may be why things like you and me have billions of photoreceptors, well, millions of photoreceptors. Um, um, and that means that there exists a scale of self-organization which can effectively be read as the internal and blanket states. You can ignore the random fluctuations. You have to make that assumption when you want to invoke the expected free energy as a description of self-organization. Not everything looks as if it plans and tries to minimize its surprise in the future, but things like you and me do. I think simply because we can do this sort of coarse graining. It hasn't answered your question, has it? I'll go and worry about pool tables.
No worries. I mean, one question, but I think you answered pretty well. But the other way to phrase the pool table is also just kind of the Big Bang hypothesis, right? I mean, the universe is constantly expanding. So, given that you have some understanding of the universe, you could also look at it at a time lapse on on a galaxy scale, and you would also be able to tell what the direction of time is. But I think the argument here again is you have random fluctuations on at the very beginning, and that essentially cause the variation there of the
Oh, I see.
homogeneities.
Sorry. Right. So you were saying that you can always tell whether something's time irreversible, even with, yeah. I think the time irreversibility comes from the solenoidal part. So yes, that's absolutely true. You wouldn't need the stochasticity to have time irreversibility. I thought you were saying where have all the random fluctuations gone? I was answering the wrong problem.
So the good answer that was still very interesting, but yes. We could ask if you have time for one question from the chat here. Adam was asking, are there relationships between centripetal hierarchical time and the centripetal structure of global workspace architectures?
I think very interesting question. I think you'd have to argue that empirically. My guess would be absolutely yes. That just my knowledge of functional anatomy means that if you associate the global neural workspace with certain parts of the brain, these are usually a multimodal association and have also have a description in terms of intrinsic brain networks that are certainly associated with processes that have longer timescales, such as sort of working memory, and indeed whose dynamics themselves are usually have longer correlation coefficients and time constants. So my guess is absolutely, but I think you'd have to commit to the parts of the brain that were the substrate that supported the global workspace, and then point to empirical evidence that at many levels these things show a a slow kind of dynamics, which would normally be lots of could be cast as semi-Markovian. They have memory, basically, very much like the sort of you know, carrying your history on the backs on your back, which immediately says that you'd expect these parts of the brain to be those that are involved in working memory from a sort of cognitive science perspective.